controller array network, or CAN bus, is an asynchronous network that uses arbitration to determine bus access. Most applications use an ISO 11898 physical layer, which is a two-wire differential twisted pair providing common mode rejection to protect against EMC. In automotive applications, it connects powertrain components like engines, transmissions, and brakes, or other devices like door locks, instrument clusters, airbags, and so on. Since the CAN identifier and data fields are user-defined, viewing more than just the trace can provide good insights. For this video, I'll be using a 2-series MSO, but the setup and operation is identical on several series of Tektronix oscilloscopes, all of which can be equipped with CAN bus decoding and triggering. On channel 1, I have the CAN high signal connected. To decode this signal, let's add a CAN bus. I'll change the bus type to CAN, verify the source is set to channel 1, set the threshold to 3 volts. Under signal type, you can select CAN high, CAN low, or differential, which would use a differential probe. I'll choose CAN high. Next, verify that the CAN standard is set to CAN 2.0. Verify that the sample point is set to 75%. This is the point where the bit is actually measured, typically far back in the bit, not in the middle. Also verify that the bit rate is set to 500 kilobits. Select bus and waveforms as a display format. Set decode format to mixed hex. Now that I've configured the CAN bus, I'll look at the decoded bus. The green bar symbol represents the start of packet. ID packets are shown in yellow boxes. Data packets are shown in cyan boxes. The DLC and CRC are shown in purple boxes. End of frames are shown in red boxes. The red bar symbol represents the end of the CAN frame. Missing acts, if present, are shown as red exclamation marks. I can also leverage the results table to analyze the decoded signal. To add the results table, I'll go to the Bus 1 configuration menu and turn on the results table in the upper right corner. If I tap one of the rows in the results table, notice the zoom box in the waveform is repositioned to correspond to the selected row. To close out the results table, I'll press the X. When debugging a system, it is helpful to capture the state of key signals when certain events occur. I'll show you how to trigger on specific content sent over the CAN bus. First, open the trigger menu and select Bus for trigger type. Verify the source is set to Bus 1. I'm going to trigger on identifier in either direction with the identifier format as standard. I'll input the identifier value as 757 hex. Now that I've configured our trigger, let's test it out. If I zoom into the trigger point, I can see that it is right after ID 757. Once I have acquired a serial signal, it can be helpful to find all occurrences of certain events. Let's see how I can do this with the search function. First, tap Search to add a new search. Then set search type to bus. And finally, confirm the source is set to Bus 1. By default, Mark on Start a Frame is selected. Now that I've configured the search function, let's start acquiring data. If I stop acquisition, I can see several points marked by the search function. In the search box to the right, I can see 10 events have been marked. As expected, all the pink marks are aligned with the start of frame. I'll take CAN decoding just a little bit further by applying a DBC file. A DBC file is a common database structure defining the ID and data of the message in the engineering units. I'm going to change the decode format to symbolic and select the DBC file. Notice in the bus decode results window, the identifier may now have readable names and the data field could be segmented into the signal and decoded. The same is true for the waveform view. The name is displayed and the 8-byte data field is segmented into the signal length. Whether you're troubleshooting complex embedded systems or designing new features for electric vehicles, Tektronix MSOs will be a great help for all your CAN bus decoding and analysis needs.